In this video, we'll discuss properties of the complex exponential function. So, we define the complex exponential of z, which is just e to the z, is going to be e to the x plus iy, which is e to the x, and then e to the iy is cosine y plus I sine of y. Okay, so that's our definition of a complex exponential, right? And so now what can I say? So the first thing we know is we know from previous video that this is a 2 pi I periodic. So note, this is exponential of z is 2 pi I periodic. So it's a periodic function. Okay. It means that the solutions to one equation of the exponential is going to be infinitely by 8, which is awesome. Okay, so now here's the first thing. So let's first define what the modulus is. So here's the first proposition. We're going to do a whole bunch of propositions with this over here. So proposition 1 is that the modulus of the exponential of z is just going to be e to the x. Okay? Here's the proof. So I have the square root of what? Of e to the x cosine y squared plus e to the x sine y squared. That's, of course, the modulus of the exponential of z, right? This, of course, is just going to be the square root of e to the 2x cosine squared y plus e to the 2x sine squared y. And then, of course, I'll just pull the e to the 2x out, so that gives me an e to the x, and then times 1, and that gives me e to the x. So that gives me the first. Here's the modulus of the exponential of z is just e to the real part, right? So in other words, we can concisely write this as the modulus of the exponential of z is just going to be e exponential of the real part of z, like that. Excellent. Okay. What's the next opposition? That proposition is that it's going to be follows a statement rule from ordinary calculus, so that e to the z1 plus z2 is going to be e to the z1 times e to the z2 for a couple of numbers. Good. So here's the proof of this fact. Proof. Okay. And so, of course, this is going to be e. I'm going to write the z1 is x1 plus I y1 plus x2 plus I y2 is e to the real part's going to be x1 plus x2 plus I y1 plus y2. Great. So this is going to be what? This is going to be, I'll write this in the following way, e to the x1, e to the x2, because I can pull, that's a real term over there, I can pull that out, right? It is that factorization. And then we're going to have what? We're going to have the cosine of y1 plus y2 plus I, the sine of y1 and then y2 plus y2. And so this is just going to be what? This is going to be e to the x1, e to the x2, and then what? And then cosine of y1, cosine of y2, minus sine of y1, sine of y2, plus I, and then sine of y1, cosine of y2, plus what? Plus sine of y2, cosine of y1. Excellent. That's a huge mess over there, but now let's look at this over here and then figure out what e to z1 times z2 is, right? So on the other side, so this is what? All this expression over here is exactly just the left-hand side, right? Left-hand side of the proposition. Let's look at the right-hand side of the proposition. So what's the right-hand side of the proposition? The right-hand side of the proposition is what? It's going to be e to the x1 and then cosine of what? Cosine of y1 plus I sine of y1. Okay, that's this term over here. Times e to the x2, that's a real number, times what? Times cosine of y2 plus I sine of y2, like so. Beautiful. And now I'm just going to fill these x1s and x2s to the front. So x1, e to the x2, and let's FOIL this out. So I have a cosine times cosine. That's going to be a cosine y1, cosine y2. And then I gives me a negative sign. So that's a negative sine y1, sine y2. Those are the real terms. Plus what? Plus I, the imaginary term. So I'm going to have a cosine y1 times sine y2. That's one of the imaginary terms. And then a cosine y2 sine y1 plus cosine y2 sine y1. That's another term over there. Now, if we relate these things over here, we see exactly that this expression over here and this expression are identical. So we just proven our proposition over here that this expression over here is true. So those are two of the most fundamental results for these complex exponentials. Now, of course, what we can do is we can ask the question, so what properties of exponentials translate? So in other words, one easy consequence of this, and one final proposition, which is a corollary of this, is if I look at e to the z times e to the negative z, then what's e to the z times e to the negative z? Well, you might think that's just going to be 1. Let's check, right? Well, according to this proposition, this is going to be e to the z minus z. But e to the z minus z is e to the 0, and e to the 0 is just equal to 1 over here, right? So in other words, the inverse of e to the z, so this implies that e to the z inverse is e to the negative z, right? And so in particular, you can use the same result to prove that e to the z to the power lambda is e to the lambda z, which is going to be a very important thing in the future. Now, there's certain restrictions on what lambda can be in that situation. You have to be a little bit careful. You can't just directly apply the rules for regular exponentials. So what's one of the morals of this, right? So the moral of this is that the rules for exponentials are all lining up the same way, but you have to carefully prove them. So just note, carefully prove all identities in the complex case. Just because an identity is true in the real case, most of the time by the identity principle or by analytic continuation, the result will be true in the complex plane. But just caution has to be observed, because if you, for example, if you raise something to a fractional power, raising something to a fractional power involves taking square roots, and taking square roots involves taking branch cuts and using logarithms. So oftentimes you get into little bits of issues when you might say, well, is it true that e to the z to the power lambda is equal to e to the lambda z? The question is be careful what the particular value of lambda is, because it might involve taking a branch cut, right? And when there's a branch cut involved, identity is not necessarily true for all values of z. So what I've been doing over here is I've been doing things that are true for all values of z, identities which remain true for all values of z. In further videos, we'll talk about branch cuts of logarithms, inverses of these exponential functions, and then see how those branch cuts affect the domains on which the identities are true. Thank you very much.